Fine. Thank you. Thank you. So, if I'm not wrong, we had in our lecture 1 and lecture 2, we had a discussion something about the component of a vector. So, let me take blue. So, if x bar and g bar, if you are more specific, let me put x of t and g of t in signals perspective. Are two signals are two vectors, then the component of the component of g bar along x bar, I can write over here g of t along x of t is given as, so we define this as c, which is equals to g bar dot x bar divided by mod g mod x bar whole square. So that is x bar dot x bar. Of course, in the signal domain, actually in the case of signals, we are supposed to define in an interval t. So let me put that black color in an interval. Let me put t1 comma t2. In that case, you are going to have c is equals to integral t1 to t2 g of t x of t dt divided by integral t1 to t2 x square of t dt. Next, this is about the component of a signal, the component of one signal along the other signal. Next, we try to define the correlation coefficients. Normalized correlation coefficient. Normalized correlation. How similar two signals are or two vectors are. Normalized correlation coefficient. Okay, let me so coefficient. Normalized correlation coefficient, we define it as Cn. In the case of vector, Cn is equals to cos theta, which is equals to g bar dot x bar divided by mod g bar mod x bar. And this will ensures you to have the correlation coefficient lying between -1 and +1.
Sir, we are unable to see your screen, sir.
So you're too late, yeah. I already shared it. Present now.
Just now stop, sir.
A window. Now is it okay?
Yes, sir.
Okay, thank you. So normalized correlation coefficient, if you try to look into, so we are going to have the normalized correlation coefficient, which is defined something like this. I think someone has joined. Let me check it out. Yeah, Aditya Mehta. So now when a Cn is equals to 1, Cn is equals to +1, more, I mean, the two vectors are similar, and Cn is equals to -1, dissimilar, exactly opposite, I can say, opposite. That means if one vector is in this direction, another vector will be in this direction. Opposite or dissimilar. And then when Cn is equals 0, we can able to say that the two vectors are orthogonal to each other. As I told you, friends, strangers, orthogonal means strangers, orthogonal. And these are foes. Okay, orthogonal to each other. So we have a similarity. We had a discussion a long time before. Now, if you try to apply the same thing for signals perspective, in the signals perspective also you're going to have a similar equation. So Cn is equals to 1 by root EG EX, energy of the signal, EG EX integral minus infinity to infinity, integral minus infinity to infinity, you are going to have g of t x of t dt. So g of t x of t dt, that's what we are going to have. Okay, and here also you can check it out that the normalized correlation coefficient lies in between, or it also satisfies this condition. Even for this case, it's also, it is going to satisfy this condition. And uh, see, it looks a little strange when you try to apply the similarity for signals, because two signals are said to be similar in the sense we are going to have more correlation. When Cn is equals to 1, Cn is equals to 1 plus 1, that means the signal g of t and x of t are more similar, and is equals to minus 1. So minus 1 means Cn is equals to minus 1. I can say able to say that the signal g of t and x of t are orthogonal to each other. So from here I can able to assess a condition which is called condition for orthogonality of two signals. So condition for orthogonality of two signals. Condition for orthogonality of two signals. This also we defined earlier. Just a recap, because I just want to orthogonality of two signals x of t and g of t. If I try to put, since we are using black for signals, integral minus infinity to plus infinity x of t g of t dt is equals to 0. If it is the case, then you can say that those two signals x of t and g of t are orthogonal. And this is called the correlation coefficient. Till now we have seen about the correlation coefficient. Coefficient Cn, in other words, normalized correlation coefficient. Normalized correlation coefficient. Next, there is a problem with this normalized correlation coefficient, because we are going to take, particularly for the signals. What is the problem? Is when two signals which are of course similar to each other, but delayed in the sense one signal, delayed in the sense one signal, this we already discussed. So if I have a signal something like this is one signal, and if the other signal is, let this be some x of t, and let this be some t1 to t2. And if I have another signal which is something like this, so t1 plus tau to t2 plus tau, and let this be g of t. And if I try to calculate the correlation, normalized correlation coefficient, that means Cn is equals to 1 upon root, since we are using black, let me continue to see, and 1 upon root Ex Eg, the energy of the signal, of course, let this be 1, and let this also be 1. So integral minus infinity to infinity x of t g of t dt, which is equals to some energy you'll be getting over here. So that energy, if I try to substitute over here, 1 upon root Ex Eg, and now we are going to multiply x of t and g of t. So if I try to consider t1 to t2 limits, this signal g of t will t1 to t2 limits. Let me assume this is 1, t1 to this is t1, and this is t2. So that means you are going to have 0 over here. G of t is 0, and x of t is going to have some value. So ultimately, you are going to perform integration of some 0. So which is equal to 0. That means it says that there is no correlation between, or it says that these two are orthogonal to each other. But exactly these two are not orthogonal. Of course, the two signals are very similar to each other, except for there is a time delay. So for that reason, a new correlation coefficient, or in other words, you can say that it is a correlation function. Correlation function is defined, and the correlation function is defined as, now a new thing is defined that is called correlation. I hope you understand the problem what I'm trying to express over here, because x of t is 0 at one point where g of t is non-zero, and g of t is 0 at a point where x of t is non-zero. And if I try to perform the product of these two signals, you will be getting 0 everywhere from -infinity to +infinity. And for that 0 signal, if you try to perform integration from -infinity to +infinity, you will be getting 0 only. But to be frank, the signal x of t and g of t are both are similar, and the only difference is the time delay. So for that reason, a correlation function is defined. So correlation function is defined, and the correlation function says that of course it is going to be represented with psi, and we are going to calculate the correlation between g of t and x of t. And now it is a function of time delay tau, integral -infinity to +infinity. Of course, these are the limits for t is equals to -infinity to +infinity. X of t plus tau into g of t, you can do it, dt, and this is also equals to if because this satisfies the commutative property, which is equals to -infinity to +infinity x of t g of t plus tau dt. So that means you're going to calculate the product between x of t and g of t. You're going to calculate x of t, product between x of t and g of t, and every time when you try to calculate, it will be a function of tau. Function of tau means what happens? So if I try to shift this g of t from -infinity to +infinity, if I try to shift this g of t from -infinity to +infinity, and whenever this g of t gets matches, whenever that g of t, so let me assume that this is my g of t. So here you'll be getting psi z x of t 0, and if I try to move towards this side, whenever it reaches to this particular point, whenever these two gets overlapped to each other, there you'll be getting maximum. And if before this you'll be having a value something like this, that means there will be a little bit less area. And if I try to go to the left side, that means I can able to say that the cross correlation between this g of t and x of t will be having the shape something like this. So it will be having the shape something like this. This is psi g x of tau, and the most important thing is here this is a function of tau, and where it is going to occur the peak value means, for suppose this is 0th position, and 0th position 0 to t1. So because at a tau is the right shift, let us assume that it is going to have right shift at a t, so that means even if you try to consider 0th location as, if I try to consider 0th location as somewhere over here, let me assume this exactly at the center. If I consider this is 0th location, and this is at some, let this be t1 to t2, okay, let this be some tau, okay, then obviously the peak is going to okay, let me tau means tau naught, let me assume, because tau is a variable, so you are going to get peak at tau naught. So that means if you try to calculate the cross correlation between x of t and g of t, you are not only finding out at which time instant, or at which time delay, at what time delay these two are similar, you are going to find out the peak value also. Peak value in the sense whether those two are correlated or not, that you will be finding out. Two things you are going to find it out using this correlation function, unlike the correlation coefficient. Correlation coefficient will lets you know whether the two signals are similar or not. Here you will find out whether the two signals are similar or not, but at the same time you will be finding out at what point of time these two signals are similar. That also you can able to extract from the correlation function, and that is the reason why correlation function, which is represented with psi of tau, actually tau is the time delay of the signal, okay, time domain of time delay of the signal that you are going to have. So this is extra information that you are providing, and hence we all this correlation function is more predominantly used if at all you would like to find out the similarity between any two signals. If you would like to find out the similarity between any two signals, correlation function is widely used. Okay, yeah, let me move on. Let me move on now. As I have indicated over here, so psi g x of tau is equals to, and of course that energy terms usually we discard. Energy terms usually we discard in this correlation function definition. Now energy fine. Now if I try to make x of t and g of t both are same, that means you'll be having a function psi z of t, psi g of tau, which is called the autocorrelation function. Autocorrelation function. So what is the benefit of this autocorrelation function? And of course, what is this autocorrelation function? First, we will try to find out. So size Gz of t is equals to integral minus infinity to plus infinity x of or g of t plus tau dt. Okay, g of t plus tau dt. So remember one thing here, since we are going to perform the integration with respect to it, that means you are going to calculate the area under the curve. Area under the curve. For suppose if I have a signal something like this, one signal something like this, other signal something like this, if you would like to calculate the correlation between these two, we are going to do the product between these two. We are going to multiply these two, and then you try to calculate the area under the curve. So if I try to, if for suppose, let me assume that this is 1 and this is 2 and this is minus 1, and let me assume this is plus 1. So at this particular point, without any time shift, if I try to calculate the cross correlation between these two signals, that means you'll be getting psi of 0. That means that tau is equal to 0, you'll be getting 0. Now when I try to move this towards the right side, so then the signal will start getting overlapped, and after multiplying, this multiplied with this portion will becomes 0, because this is 0 for one signal, it is 0, and for another signal there is some amplitude. So if I try to multiply the 0 signal with this portion, you will be getting 0 only. So only portion that is left out for non-zero value is this one, a simple triangle. Of course, so if this is one multiplied with this triangle, you will be getting some area. So based on the shift value, that means based on the tau value, you will be having some function. So this is nothing but your cross correlation between two signals. Now when I try to substitute this for the same signal, that means you will be getting autocorrelation. Autocorrelation means if I have a signal something like this, the previous example if I consider, which is located at 0 minus t and plus t naught and minus t naught plus t naught. Let me take the same signal, and then again I'll put minus t naught 0 plus t naught. And what we are going to do, we are going to calculate the correlation between these two. First, let us try to consider tau is equals to 0. Tau is equals to 0 means without shifting, you just try to product these two. So if I try to multiply these two, you'll be getting, if this is 1 and this is 1, you'll be getting only 1. So minus t naught 2 plus t naught, and if this is 1, you will be getting area under the curve. So you will be getting this. If I consider this as this is 2 t naught and this is 1, and so the area will be 2 t naught. So size z of 0 is equals to 2 t naught. Now if I try to move 1 to the right side, then what happens is, what I mean to say is, at tau is equals to 0, you are going to have the maximum value, that is 2 into t naught, and then if I try to move this to the right side, slowly the overlap region area will goes on reduces, and hence the area will slowly reduces to something like this. And the moment when it reaches to this t naught, that means when the shift goes to t naught, then both will be disjoint, and hence you'll be getting 0. So here also at minus t naught you'll be getting 0. So this is what the autocorrelation function. This is what the autocorrelation function is. What is the significance of this autocorrelation function? Autocorrelation function, if you try to apply the Fourier transform for autocorrelation function, Fourier transform for autocorrelation function will be giving you the power spectral density. Power spectral density means power per unit bandwidth. Power per unit bandwidth you are going to get if I try to follow this. Okay. Now the most yeah, you can able to prove this very easily. That means the Fourier transform of psi zz of tau, psi zz of tau is equals to Fourier transform of psi zz of tau is equals to, you will be getting the power spectral density. Power spectral density means it will be the spectrum psi gg of f you will be getting. So is equals to psi, of course, gg you can able to write psi gg of f, psi gg of f, which is equals to mod g of omega whole square. Mod g of omega whole square means if I try to have the Fourier transform of g of t, okay, for that matter, many people, I think few people might be knowing what is this Fourier transform. Fourier transform of g of t is equals to g of omega, Yeah, if there are third years and final years, they might be getting confused with small omega and capital omega. But in general, we will be considering a small omega. So that is the reason why I kept here small omega. Then the Fourier transform of the correlation autocorrelation function will be the power spectral density, that is the square of the power spectrum. So as per the Pascal's relation, as per the Pascal's relations, you are going to have the power in the frequency domain is equals to the power in the time domain. So power in the frequency domain is equals to power in the time domain, means you will be having the energy of the signal. Energy of the signal Eg is equals to integral minus I'm sorry, I'm talking about the energy, not the power. Mod g of t whole square dt is equals to mod g of t dt is equals to integral minus infinity to plus infinity mod g of omega whole square. Of course, there will be a parameter 1 by 2 pi here, and then d omega will be there. D omega will be there. Okay, now this is about the autocorrelation function, and much more of this autocorrelation function. See, for deterministic signals, the autocorrelation function and power spectral density, this is called the power spectral density, psi gg of f. This is called PSD. PSD means power spectral density. The significance of this power spectral density is very, very high in the case of random signals or undeterministic signals or random signals. Why is there it is very difficult to calculate the power of the random signal, very difficult to calculate the power of the random signal, but because the signal is random in nature. If a signal is random in nature, how to calculate the power of the signal or energy of the signal? It is a little difficult, right? So in such situations, what we will try to do is we will try to calculate the autocorrelation function. So once we calculate the autocorrelation function, and if you calculate the Fourier transform of the autocorrelation function, you will be calculating the power spectral density or energy spectral density. Okay, so power spectral density for power signals, energy spectral density for energy signals. Energy signals means all periodic signals are power signals. Okay, so if the signal is extended from minus infinity to plus infinity and has some periodicity property, then you can consider that it is a periodic signal. A periodic signals usually comes under the energy signals. Okay, so that is the things what we have discussed so far. Of course, I completed half of the duration. Now today what I'm going to do is I will be talking something about signal representation by orthogonal signal set. Signal representation by orthogonal signals. So this is a new topic that I'm going to teach now. Signal representation by orthogonal signals. So before going to talk about this, wherever there is a signal, I can even write the conventional black. Let me use, or if you want to be blown. So vector, vector representation by orthogonal set of vectors. Orthogonal set of vectors. So what does it mean? What it means is, if you have any vector in free space, let it be some f bar, which is going to have some fx into ax bar plus fy into ay bar plus fz into az bar. Actually, these ax bar, ay bar, az bar are also vectors. Ax bar, ay bar, and az bar are also vectors. So here, the vector in free space f is going to be represented by orthogonal set of vectors. You try to remember, see, ax bar, ay bar, and az bar. These three are orthogonal in nature. Okay, so orthogonal itself doesn't sufficient. Actually, whenever you are going to represent a vector in terms of a set of orthogonal vectors, the most important point for exact representation. What do you mean by exact representation? Of exact representation or accurate representation, if at all you would like to represent a vector in terms of the orthogonal set of vectors, that vector set should be a complete set of vectors, complete set. I think much of the discussion related to this complete set we had, maybe if I'm not wrong, in the very first lecture or maybe in the second lecture. So okay, I can represent this vector in terms of only ax bar and ay bar. If I do that thing, then if I try to calculate the error, let me assume that my f bar approximation APPROX, I'm considering only the two unit vectors, that is fx into ax bar plus fy into ay bar. If you calculate the error between these two, there will be some error. The error will be 0 if at all, if you have a vector f bar. If you have a vector f bar, the representation of this vector in terms of the set of uh, unit vectors ax bar, ay bar, ay bar, you can represent this vector. If you want, you can represent it with ay bar, az bar also you can represent, and then if you want ax bar and az bar also you can represent. Yeah, that is also possible. And if you want, you can represent, or if you can able to approximate the vector f bar in terms of ax bar alone, or ay bar alone, or az bar alone, you can able to approximate with these alone. But in all these approximations, the representation of the vector f bar uh, with az bar alone, or ay bar alone, ax bar alone, or ax ay, ay az, ax and az bar, in all these cases there will be certain error. Error means the approximation of this vector f bar with the actual vector. If you try to calculate, there will be some error. So the error will be minimum or 0 if and only if the representation basis, actually these are called basis vectors. These are called basis vectors. So if at all the basis vectors are a complete set, then the error will be 0. That means f bar minus f bar approximate, which is equals to the error E is equals to 0 if the basis vector set is complete. If the basis vector set is complete, then only you will be having the exact representation. Whether you go with the Cartesian coordinate sets ax bar, ay bar, az bar, these are called the basis vectors, unit vectors. Or if you want to go, this is Cartesian coordinate system, Cartesian. And if I try to go with cylindrical, if I try to go with cylindrical, then we are going to have the vectors a rho bar, comma a5 bar, comma az bar, and these three also form the complete set. That means you don't find another unit vector that is perpendicular to all these three. So if you try to consider ax, ay, az, can you find out another vector that is perpendicular to these three unit vectors? No, you will never find it out. So if that is the case, then you can say that ax, ay, az forms a complete set. In a similar manner, a rho, fi, az also forms a complete set. And following the spherical coordinate systems, you are going to have a r bar, comma a theta bar, comma a phi bar, r theta phi. Okay, this is a complete set, this is a complete set, this is a complete set. Now when we try to apply a similar concept, when the same concept for the signals to exactly represent a signal, x of t, or for that matter x of t or f of t, if I have a signal x of t or f of t, and if I would like to represent in terms of another signals, first of all I should find out a set which is complete in nature, and not only complete, it should also satisfy the orthogonality principle. Here ax is orthogonal to ay is orthogonal to az is orthogonal to ax. That means ax, ay, az both are mutually orthogonal to each other. So you are supposed to find out a complete set of signals and also a complete set of signals that are orthogonal to each other. Orthogonal to each other. So if you try to find out that complete set, then it is possible to represent a signal by the complete set of orthogonal signals. Okay, now let me ask you a question. When you start the signals and systems, okay, for finally, yes, I think I taught this, I think I didn't taught the signals and systems to anyone over here, I think, yeah, somewhere at any department I taught. So what is the very first fundamental signal that you study in signals and systems? What is the very first fundamental signal that you study in the signals and systems? That is the question what I'm asking. Anyone?
Sir, unit step signal.
Actually, unit step signal is the second signal, if I'm not wrong, and the very first signal
impulse signal.
Impulse signal. So, can Okay. Okay. So okay, let me check it out. Let me check it out. Fine. Let me assume, since we can talk in a continuous domain or discrete domain also, delta of t. Delta of t. Delta of t, actually the basic, okay, let me give the definition of the impulse function and then we will be entering into the signal representation. So impulse signal delta of t is equals to 0 for t is not equals to 0 and is equals to is undefined. I cannot write undefined at t is equals to 0. I cannot say any value. And one more condition is there. Integral minus infinity to plus infinity delta of t dt is equals to 1. Delta of t dt is equals to 1. So usually it will be represented with something like this. And usually this doesn't mean that the value at 0 is equals to 1. Okay. Sometimes the definition also will be something like this. So what they'll try to do is limit some delta t tends to 0. So what they'll try to define a gate function something like this. So here 1 by delta t plus minus. So it's not 1 by delta t, I think it is only delta t. Yeah, let me write it out. Minus delta t by 2 plus delta t by 2 and delta 1 by delta t, because this distance is delta t, 1 by delta t is the amplitude, and for this gate function you apply limit delta t tends to 0, then you'll be getting this one. Okay. Okay, fine. So this is the definition for the impulse function. And if I try to define the same for a discrete impulse, then I can able to say that delta of n is equals to 1 for n is equals to 0 and is equals to 0 for n is not equals to 0. And you don't find this type of expression in the case of a discrete impulse. So the impulse will be something like this. So if this is 0 and this is 1, this is a discrete impulse. This is discrete impulse. Now approximating a signal g of t approximating a signal g of t over the interval t1 comma t2 by a set of n mutually orthogonal signals x1 x2 and so on xn. Okay, let me write this thing. So I would like to approximate the signal g of t. That means you are going to have a signal representation in terms of n. I'm considering some n fixed. Earlier, in the case of vectors, we are going to have this n as 3. So ax bar, ay bar, az bar. If it is cylindrical also, you are going to have 3. N is equals to 3. Spherical also, n is equals to 3. So I am going to consider n mutually orthogonal signal set. Mutual n in terms of n mutually orthogonal. Mutually orthogonal and mutually orthogonal set. Set means set of signals. So I'm going to have n mutually orthogonal. Mutually orthogonal means if I apply the same concept in the case of vectors ax bar comma ay bar comma az bar. Ax is ay are orthogonal to each other, ay az are orthogonal. So that means if you try to find out anyone over here in this particular n set, so let me assume the set is x1 of t comma x2 of t comma x. So let me assume this is the set x3 of t and so on up to x x n of t. So mutually orthogonal signal means you choose any one of the signal from this set. Let me assume x p of t and try to correlate this signal with xp of t with all remaining all signals. You will be getting a correlation coefficient or correlation value 0. That means you can able to check it out. Integral minus infinity to infinity x p of t multiplied with x I of t. For I is equals to for I of t for I is equals to 1 gamma 2 and so on up to up to up to n, and this should not include I should not be equals to p. So in such cases you can able to say that the signal set is mutually orthogonal set. Mutually orthogonal set means you try to find out a signal in that and then get the correlation that with of that signal with all others. You will be checking out that those all are orthogonal to this signal xp of t. So in such cases, if that is the case, then you can able to write because you are going to represent the signal g of t. So you can able to write g of t can be approximated as c1, which is a coefficient that you are going to have x1 of t plus c2 x2 of t plus c3 x3 of t and so on plus cn xn of t. Now initially we have taken a set of n mutually orthogonal signals, assuming that that is a complete set. Then you can able to represent something like this, and this is nearly equals to summation ci xi of t for I is equals to 1 to n, and we define this for the interval interval t lying between t1 and t2. That means we are going to approximate the signal g of t with this mutually orthogonal set over the interval t1 and t2 only. The energy of the signal. Now if you try to calculate the energy of the signal, error signal E of t, energy of the error signal E of t, then E of t should be equals to g of t minus summation I is equals to 1 to n ci xi of t, ci into xi of t. And it is very easy to calculate the coefficient cn value. It is very easy to calculate the coefficient cn value. So the value of cn, which is nothing but the coefficient, cn is equals to integral t1 to t2 g of t x of t dt divided by integral t1 to t2 x square of t dt. This is the component of one signal and another signal. This we already defined. Okay. One point I would like to say over here. I just want you people to look into this equation once again. So here the signal g of t we try to approximate it in terms of the n mutually orthogonal signals. Now if you try to look into that equation, the equality, so this means okay, fine. So if that n mutually orthogonal set is, if n mutually orthogonal set is complete, complete, then I guess very straightforwardly can write instead of nearly equal to, I can straight away write this. I is equals to 1 to n Cn. Sorry. This is Ci actually. So Ci xi of t. If this is most important, and hence because this equals to sign why we are writing this equals to sign why we are writing because E of t is equals to 0. If you try to calculate the energy, E of t is equals to 0. So energy E of t is equals to 0. It doesn't mean that the signal at each and every point in the right side, that means the right side signal and left side signal both represents the same at each and every point of time t. That is wrong. Okay, what I mean to say over here is energy E of t is equals to 0. The energy of the difference between the two sides of the equation approaches to 0. If equality exists in ordinary sense, the error is always 0, but the converse is not necessarily true. See, at each and every time t, if both the signals are same, no doubt you will be getting the error E of t is 0. But error E of t is equals to 0 doesn't always mean that the signal in the left side and signal in the right side will be the same at each and every value of t. Actually, what E of t is equals to 0, that means actually it is not E of t, it is the energy of E of t is equals to 0. Energy of E of t is equals to 0. I'll try to repeat this thing once again. What I mean to say is, so we are going to say that the energy of error signal is equals to 0. Energy of error signal is equals to 0 will occur in two cases. One case is if the error signal is completely 0. Error signal is completely 0. Error signal is completely 0 means the approximation, the representation and the original signal both were same at each and every value of t. In that case also you are going to get the energy of the signal is 0 because E of t is equals to 0. But there are the cases when there will be some positive error and some negative error. Some positive error and negative error. So in such situations, if you try to calculate the energy of the error signal, the positive error will get cancelled with the negative error and hence the energy will goes to 0. That is also one of the important cases that you're supposed to calculate. Consider. The error energy can approach 0 even though E of t, the difference between the two sides is non-zero at some isolated instance. This is because even though E of t, the difference between the two sides is non-zero at some isolated instance, as such the area under curve E square of t is still 0. That means there will be a case when you try to calculate the energy area E square of t area, if you try to calculate, then if it is equals to 0, if it is equals to, for suppose, let me assume that E square of t, because energy of the error signal means you are supposed to calculate E square of t. If for suppose the square of the energy waveform something like this, so let me assume this is E square of t graph. So this area will get cancelled with this area. So that means if I try to calculate integral minus infinity plus infinity E square of t, you will be getting 0. That means sometimes there will be a positive error, sometimes there will be a negative error. In such situations also you are going to have the energy of the sigma E square of t will be goes to 0. Okay. Now were there any set? Now the question is, I would like to represent a general signal g of t in terms of some complete set. How many different types of complete sets that do exist? How many different types of complete sets that do exist? So that is the question that is being asked now. So how many types of different so one such thing is the trigonometric Fourier series. So trigonometric Fourier series says that you can able to represent, you can able to check it out over here. Some examples of some well-known signal sets that are mutually orthogonal to each other. The complete sets are trigonometric sinusoidal functions, exponential functions, Walsh, W-A-L-S-H, Walsh functions, Bessel's functions, Legendre polynomial, Lagrange's polynomial, Jacobi polynomial, Hermitian polynomials, Chebyshev polynomials. What all are these things? Okay, if I try to say Cartesian coordinates, cylindrical coordinates, spherical coordinates, what are these things? These all are different coordinate systems. That means these all are different sets of unit vectors that are mutually perpendicular to each other and forms a complete set, which indicates that any vector in the free space can be represented in terms of any of these three vectors, any of these three coordinate systems in a similar manner. So there are a complete set of signal set. See, we would like to have a complete set of signals. Complete set of signals for signal representation. So for the signal representation, we should have the complete set. And the second thing is, all the signals should be mutually orthogonal to each other. All the signals should be mutually orthogonal to each other. So if that is the case, how many types of such signal sets do exist? Okay, the one that was given over here is, the first one is trigonometric set. Sinusoidal signals you can take. Exponential functions. Exponential functions is another set, something like cylindrical coordinate systems. You're going to have exponential functions. Walsh functions. We can find out what is Walsh functions. Bessel's functions. Legendre polynomials. Lagrange's functions. Jacobi polynomials. Hermitian polynomials. Now, and Chebyshev polynomials. Okay. Now, what I'll try to do is, I'll try to list out over here those different types of orthogonal set. Different types of orthogonal set. I think you can able to see my screen, right? The Word document is clearly visible. Okay. So yeah, let me put it somewhere.
Sir, sir, we are unable to hear, sir.
Yeah, dear students, any problem happened? Hello, is there anyone over here?
Your voice got stuck, sir.
So now is it okay?
Sir.
Is my screen visible now?
Yes, sir.
Sir.
Okay, thank you. Now I'm giving a small task for my enthusiastic signal processing learners. The task is, I am giving you different sets of signals. I'm giving you some sets of signals, and okay, cos 2 into omega naught, cos 3 into omega naught t for some value of omega naught, plus and so on. So that means 1 cos and then plus sine 1 into omega naught t, comma sine 2 into omega naught t, and so on up to infinity. This is infinity terms and this is up to infinity terms. So this is one complete set. So that is trigonometric sinusoidal functions. This forms a complete set. Not only complete set, it is mutually orthogonal to each other. Mutually orthogonal to each other. What do you mean mutually orthogonal to each other? Okay, let me consider some function in this particular thing. So let me consider sine p omega naught t. Now, if you try to correlate or if you try to check the orthogonality condition between this sine p omega naught t and all the other signals that was over here except for sine p omega naught t. Okay, let me try to do the thing. Sine p omega naught t multiplied with 1. So you'll be getting sine p omega naught t and integral minus infinity to plus infinity. If I try to do the thing, you'll be getting 0 because positive area and negative area it will be 0 only. And if I try to perform sine p omega naught t multiplied with sine cos 1 omega naught t. So cos p omega naught t and cos omega naught t sine theta cos okay sine 5 theta and cos theta. So 1 by 2 I can write. So you will be getting 2 sine a cos b. 2 sine a cos b means sine a plus b plus sine a minus b. Sine a plus b is again a sinusoidal in nature and sine a minus b is also a sinusoidal in nature and hence it is also 0. That means sine p of t, if you try to calculate its orthogonality check with remaining all the signals that was over here in this particular set it will be orthogonal only. So this is one such, and from this we have obtained a trigonometric Fourier series. Trigonometric Fourier series you are going to get. So we have Cartesian coordinates, cylindrical coordinates, spherical coordinates. Each has its own use, right? Likewise, trigonometric Fourier series is one such thing. Next, second one, complex exponentials. So complex exponential means e power j n omega naught t. So I can able to write, this is also one set, n is varying from minus infinity to plus infinity. I cannot write equal to sign. Minus into plus infinity. All integers you take, let it be integers only. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on up to minus infinity to plus infinity. So this complex exponential set also forms a complete set which is also mutually orthogonal to each other, and hence you can make use of this second set also to represent any signal within the time limits t1 and t2. Within the time limits t1 and t2, you can able to use this one also, something like another coordinate system. So from this we have obtained what we have obtained, complex Fourier series. Complex Fourier series. And remaining things were maybe little new to the people, but still I'll give it over here. I just want you people to try to represent. Okay, let me give the names and afterwards I'll give you the task. So another 3 minutes is there. So 2 terms were completed. The next third one is Walsh functions. LSH Walsh functions. I'll be very enthusiastic in knowing these things also. Even I myself haven't done, but I know the things. So fourth one, Bessel's functions. Bessel's functions. Fifth one, Legendre polynomials. Legendre polynomials. Polynomials. Sixth one, Lagrange's. Seventh one, Jacobi functions. Eighth one, Hermitian. Ninth one, Chebyshev. These are few such examples. Okay, now any one of you take one task. Okay, if I'm not wrong, there are almost 8 people over here, 8 or 9 people over here. So each one take one such set and try to represent a signal g of t in terms of these Walsh functions and what benefit we are going to get in each case. We try to assess it. Anyway, the first two, that is complex Fourier series and trigonometric Fourier series, we all know, and even I can able to explain it also. Now I want you people to voluntarily look into these different types of, this is one complete set, this is one complete set, this is also one complete set. Okay, so yeah, so you try to take any one of these, either Walsh or Bessel's functions or legendary polynomials, and you try to take one simple signal, whether it might be a sinusoidal signal or any square waveform, whatever it might be, you just try to take one simple signal and try to represent that signal in terms of these complete sets and try to find it out. You explore many signal processing textbooks are there, and you try to assess what is the benefit that we are going to have if I try to represent the signal x of t, or if I try to represent the vector x of t, x in terms of spherical coordinates, in terms of cylindrical coordinates, in terms of Chebyshev polynomials, in terms of Hermitian polynomials. So just that means first of all find out what is this complete set, Chebyshev polynomials, Hermitian polynomials, how the basis function. Actually these are called basis vectors. So each one, this is one basis function, this is one basis function, basis function, something like ax bar, comma ay bar, comma az bar. These are basis vectors. A rho bar, comma a phi bar, comma a z bar. These are also basis vectors. So likewise, you are going to have a set of vectors. So all these signals that what we are going to have is a set of vectors. Set of signals are basis signals, basis functions. So likewise, you try to find out how to generate the basis functions for all these. So 3 to 9. Okay, for 1 and 2, it's okay, fine. So someone voluntarily try to take one. Someone, let me take some person, Walsh functions. What is this Walsh functions? How to generate those Walsh functions? How to represent a signal in terms of these Walsh functions? And what benefit we are going to get if I try to represent a signal in terms of Walsh functions? Try to check it out and let me know. Okay, I'll be very happy if you try to do this thing. Okay, and go on to the Bessel's functions. Bessel's functions, what were these functions? Bessel's functions, how to generate these Bessel's functions? We have some idea on these things. What? These trigonometric series, trigonometric sinusoidal functions, and then complex exponentials. We have some idea on this. Okay, and I want you people to explore about everyone. Okay, each person you take one such signal and try to explore it. Maybe Govinith Ishta third, Maheshwari Durga fourth, Manasanara, and try to share what is your experience with me. And based on that, we may have something else also. Okay, see, this session is to educate you people. Okay, not only in the fundamentals, but also you people can able to find out what is new also. Okay, so this is a simple task what I'm giving. Okay, everyone please take one of the things that was given over here. Total 9 different types of complete sets I have given here. What was this complete set is, how these basis functions are generated, and if I try to represent a signal in terms of this, what benefit I will be getting. So try to answer these 3 questions. How to generate these signals, on what basis I should generate these signals, and if I try to represent a general signal g of t in terms of these Hermitian polynomials or Chebyshev functions, actually how to represent it and what benefit if I'll get if I try to represent it. So you try to explore these things and just discuss with me at any point of time at your free time. So I'll be talking with you, and based on that I'll be continuing my lecture in the next week. As of now, I'll be stopping the recording, and if you have any queries, I'll be addressing now. Okay, I'll stop recording now.